Gentlemen, today we're going to go over a little bit more about solutions and solubility, and we're going to discuss how we measure solutions, basically. How we measure how concentrated or dilute something is, how many particles are in whatever solvent you have. So I want to start out, and I'm going to kind of just follow this PowerPoint for the most part here. I will do some stuff uh, on the note, the smartboard note, but mostly I'm just going to follow the PowerPoint. So you can follow along with the PowerPoint or just listen. But what is happening whenever you dissolve something is kind of what you see in this little cutout circle here, where the particles of the solvent, in this case water, interact with the particles of the solute, in this case some ionic compound like sodium chloride, for instance. And the water interacts with those particles and will pull them away because they want to interact with water and they're done interacting with each other, so they'll interact with the water. However, there is a point at which the water cannot take any more particles. It's filled. All the water particles that can interact with it are interacting with it, and that is what we call saturation. So when a solution contains the maximum amount of solute that it can hold, that's said to be saturated. And that's at a constant temperature and pressure. Temperature and pressure can affect how much solute you can get into a given solvent. And the saturation point depends on what you're dissolving and what you're dissolving it in. So salt dissolved in water has a different saturation point than sugar dissolved in water. Or say salt dissolved in alcohol, if you could do that, would have a different saturation point than salt dissolved in water. So the solute and the solvent both affect what the saturation point is. And so a saturated solution contains the maximum of solute you can have. And once you get past a saturated solution, so if I added 38 grams of salt to 100 milliliters of water, that's the saturation point. The salt would dissolve, and I have a very salty saltwater solution, very concentrated saltwater solution. If I kept adding salt to that, no more salt could dissolve. And what would eventually happen is that salt that couldn't dissolve will just sit on the bottom, and some of it will dissolve because salt isn't very smart. It doesn't know I can't fit there. But as it dissolves, another piece of salt will form, or will recrystallize. So the amount of salt that's dissolved versus the amount that's crystallized stays the same. It's another situation of dynamic equilibrium, which is the same thing we saw with different states of matter in flux. So the water bottle that's half filled and closed, you have a dynamic equilibrium between water and vapor, or liquid water and vapor. And here you have a dynamic equilibrium between undissolved solute and dissolved solute. And there's actually a way you could test this at home if you wanted to, and if you had the right stuff. And it's not that. So let's take a look at an awesomely drawn example, another masterpiece by me. I really should take an art class or something. But anyways, let's say you have 100 milliliters of water in a cup, and you put into it 210 grams of sucrose, table sugar. 100 grams of water, 100 milliliters of water actually can dissolve 200 grams of sucrose. It's very soluble. That's its saturation. That's its solubility. Its saturation point. So once you get those 210 grams dissolved, and this is assuming room temperature, 25 degrees Celsius, if you added more sugar, some of that sugar would dissolve, but it would force some other sugar out of solution. And one way you could actually see this at home is if you had sugar cubes. So if you took this saturated solution of sugar and you added a sugar cube to it, regular sucrose, same stuff as in the solution, what would eventually happen is the sugar cube would sort of look like it melted, because some of those sugar cube particles would dissolve into the water, and meanwhile, some dissolved sugar particles in the water would crystallize. But they aren't going to crystallize back into a nice cube. They're just going to crystallize into kind of a mass on the bottom, grains on the bottom of the cup. So it would look like over time the sugar cube melted into kind of a puddle at the bottom of the cup. And what's actually happening is some of the sugar cube particles are dissolving, and they're kicking other sugar particles back out of the water until the whole thing is no longer recognizable as a cube because all the particles have switched places enough. And that is, again, a dynamic equilibrium. As one particle dissolves, another particle crystallizes. So you always have the same amount of dissolved particles in the water and the same amount of crystallized particles at the bottom of the cup in this instance. So dynamic equilibrium. So as I kind of mentioned there, Solubility is how much of a substance can dissolve in a solute. Uh, Generally, for us, since we're going to be talking about water as our solvent pretty much all the time, solubility is given as 100 as how many grams per 100 grams of water, or 100 milliliters of water, because water is a gram per milliliter. So sugar, sucrose, was 210 grams per 100 grams of H2O. Very, very soluble. For gases, and you can dissolve gases in water. Again, carbonation is what that is an example of that. For gases in water, it's grams per liter instead of grams per 100 grams, just because gases dissolve in a much smaller amount, so it makes sense to have that unit. And that's called the solubility. It measures how much of a substance you can put into a solvent before it's saturated. So a couple quick terms here. If a solution that contains the maximum amount of solute is saturated, a solution that contains less than that is unsaturated. And very complex. So basically, if you take an unsaturated solution and add more solute, it'll dissolve. If you have, let's say, 100 grams of sugar in 100 milliliters of water, which is halfway to the saturation point, and I add more sugar, that extra sugar will dissolve until you reach the saturation point. Another term, this is actually a term we had way back in the very beginning when we were talking about mixtures, miscible. So liquids can dissolve in other liquids. And generally when that happens, the liquids are called miscible, which means they can dissolve in each other in any proportion. And kind of the weird thing about that is we determine the solvent and the solute by what there's more of. So let's say I have a beer, and a beer is about 5% to 6% alcohol by volume. So it's more water than it is alcohol. So it's alcohol dissolved in a water solution. Now, there's other things in solution in beer. That's what gives it the taste, other parts of the plants that were involved in the making and the yeast. But it's a solution in water. It's mostly water. Now, once you get up to something like, well, anything over 100 proof. So anything over 100 proof, any alcohol over 100 proof, that means it's over 50% ethanol, 50% alcohol. Ethyl alcohol is a type of alcohol we can drink without immediately being poisoned. Once you get over that 50% mark, that means you're mostly ethanol. So that's a water solution, or water dissolved in an ethanol solution. So ethanol would become the solute, and water would become the solvent. Just kind of some weird things. But when that happens, when liquids can dissolve in any combination with each other, infinitely soluble in each other, that's just called miscible. They mix together. It's the opposite of oil and water, immiscible. Oil and water are immiscible. They can't dissolve in each other. So miscible and immiscible, we touched on these at the beginning, but if something has no solubility, to a liquid has no solubility in another liquid, that's immiscible. And if it has basically infinite solubility, it's miscible. So there are other factors that can affect solubility. Generally, if you heat things up, if you heat up the temperature, you can get more solids into a liquid solvent. So solids tend to increase in solubility as temperature increases, but not all solids, just most of them. So, for instance, you can get more sugar into hot water than you can into cold water. And we'll talk about what you can do with that. There's actually some things you can do with that chemically that are interesting. But you'll notice this chart here. There is this ytterbium sulfate actually goes down in solubility as temperature goes up. And salt, NaCl, man, it doesn't change. And by the way, the reason this is from 0 to 90, well, and eventually 100 degrees is because above 100 degrees, water is no longer a liquid. So this is pretty much the entire possibility of things dissolving in liquid water, because below that it's a solid, above that it is in fact a gas. So for the entirety of water's liquid existence, salt doesn't change. You can get just as much salt into freezing water as you can into nearly boiling water, and it's 38 grams per 100 grams of water. It will dissolve faster in the warmer water because the particles are moving faster, so they can interact with the salt more often. But it will still dissolve the same amount given enough time in like 0-degree water as 100-degree water. Sort of weird. Gases, on the other hand, tend to decrease solubility as temperatures go up. So, and we'll talk about gas and water in a second. But I wanted to cover this. Supersaturated solutions are really cool, and hopefully I'll be able to get into the classroom and do an actual demonstration of this and take a picture. But I have a series of pictures of what I would do. A supersaturated solution contains more solute than it can theoretically hold, which is kind of not possible. Like, that sounds like it shouldn't exist. And it's sort of a trick. What happens is, if you take a hot liquid, you boil water, and you make that solution saturated. Let's say you put like 300 grams of sugar into 100 grams of boiling water. Remember, at room temperature, you can only take about 210 grams. So you're putting way more sugar in there than it can hold at room temperature. Because it's hotter, it can actually hold more of the sugar. And if you get the supersaturated solution just right, you get it just right, and you cool it down slowly, and you should be very careful with these things. It's almost like the solute hasn't figured out that it can't exist like that. So as long as you leave it alone, if you let it cool down slowly, you can end up with a supersaturated solution. Everything will stay in solution, but it's really, really unstable. If you add one tiny crystal, the whole thing will crystallize immediately. So here you have, this is probably sodium acetate, this solution here. And it's supersaturated. This is what I'll do an example of. But if you add just one more crystal, so they've saturated it at a hot temperature near the boiling point of water, let it cool down, and the sodium acetate just hasn't figured out that it can't exist like that. Like, the solution's like just kind of stupid, hasn't figured it out. But if you disturb it even slightly, add one tiny what's called a seed crystal, the whole thing rapidly crystallizes. In other words, from dropping that crystal until this final picture, that's probably 5 seconds. So the whole thing will crystallize. It'll also get very warm. There's hand warmers that work on this principle. The reusable ones that you can put in the microwave and reuse, they work on this principle. They crystallize rapidly, and that releases heat, among other things. So that is supersaturated. Another place where you might see supersaturation, if you've ever made rock candy. The way you make rock candy, if you've ever done it at home or in school, you boil water and saturate it with sugar. And then you put the solution usually in a jar or something, and you either put in a stick or a string. And what happens is, as the solution cools, it's supersaturated, but because there's a string or a stick in there, that kind of disturbs it, and it'll crystallize. But it crystallizes sugar. That sugar solution crystallizes much more slowly, so it takes a long time. If you ever seen one of these crystal growing kits, that's how they work. They start with supersaturated solution, and then you disturb them by pouring them on to one of these little stands, and they crystallize very quickly and grow. So that's a little bit about solubility, supersaturated, saturated, and unsaturated solutions. And so what I'm going to talk about now is gases, and gases being dissolved in water. So for solid things dissolved in water, so solid crystals dissolved in water, whether they're ionic or covalent, solid particles dissolved in water, pressure does not affect the solubility, pretty much not at all. But for gases dissolved in water, it has a great effect. So the way you dissolve a gas in water generally is you put pressure on the liquid, pressure from that gas. So the partial pressure from the gas determines how much it will dissolve in the liquid. So if you have a pop bottles are carbonated and held under pressure. That's why pop bottles, you can't, if they're unopened, you can't squeeze them at all. They're under pretty good pressure. And that pressure of CO2 is holding the dissolved CO2 in the water. It's harder for that CO2 dissolved in the water to leave because it's being held in there by the pressure of CO2 pushing down on it. You open the pop bottle, and now CO2 can leave, and because CO2 can leave, there's a lot less partial pressure of carbon dioxide pushing down on the bottle. So eventually that pop would go flat if you don't recap it. If you recap it, again, the carbon dioxide can't leave, so the pressure will build up here as carbon dioxide particles escape the liquid, and then it'll build up here to the point where, in fact, no more particles can escape. So you can stop it from going flat by recapping it. So there's actually a law that can indicate the relationship between pressure and solubility, and it's called Henry's law, and it's a very simple law. It looks like any other gas law. It's dealing with gases. It looks like any other gas law. It's just a proportion. And all it says is the solubility at one pressure is equal to the solubility at a different pressure. And as long as you measure the pressures in the same unit, you can measure them in any unit. So an example problem would look like this. And this is, again, it's called Henry's law. Let me get back here. So solubility of a gas in water is 0.77 gallons per liter at 3.5 atmospheres. What is the solubility at 1 atmosphere? So not hard to do. You just notice you have a solubility 1, a pressure 1, a pressure 2, and you're looking for S2. So you'd rearrange this for S2. S2 equals S1 P1, or S2, excuse me, S1 P2 over P1, and you just rearrange it and solve it. I will do that and come back. Okay, and you'll see if I set it up and do the math, if this gas has a solubility of 0.77 grams per liter at 3.5 atmospheres, it would have 0.22 grams per liter. I don't know why I put atmospheres there. That's pretty terrible. I will correct that. I want the eraser here. So 0.22 grams per liter solubility at 1 atmosphere. One area where this solubility thing is really important is dealing with fish, especially non-tropical fish. It tends to affect temperate water fish a lot more. So remember, if I have water at, let's say, I don't know, 20 degrees Celsius versus water at 10 degrees Celsius, this water is going to evaporate faster. So more evaporation, and with more evaporation, also the solubility of O2 is lower. So let's say we have O2. You can have less O2 because more of the O2 is going to leave. So the O2 is going to come out. And by the way, there is, in our oceans and seas, oxygen dissolved in water. That's what fish's gills do. They take oxygen out of the water. They don't break hot water, hydrogen, and oxygen apart. They take dissolved oxygen out of the water. So in doing that, they're actually breathing oxygen. Fish breathe oxygen just like we breathe oxygen. They just breathe it out of dissolved in water. So at 10 degrees Celsius, you're going to have a lot more dissolved oxygen because O2 solubility is higher. So maybe only one of these is going out, not as many, not like 3. So you have more dissolved oxygen. Less O2, more O2 in the water. And the problem that fish are having is as global temperatures rise, and yes, that's a real thing that's really happening, water temperatures are rising too. And fish that are used to having more oxygen in the water are dying off. So fish that are used to having more oxygen in the water are dying off, and it's not affecting tropical fish as much that are used to having less oxygen in the water. But basically, there are a bunch of fish asphyxiating because there's less oxygen in the water because the temperature is higher, which is a little sad because, you know, you don't want to be killing off all the ecosystem. Eventually, that will get to us, and it would be bad for us.